Why your model sees something when there is nothing. LASSO versus decision trees versus ensembles. There are many data science and machine learning methods in the toolbox. Which one should be used depends on the context. Let's kick things off with a concrete example. Suppose an analyst is trying to predict a person's weight using a set of independent variables: age, oxygen level, run time, run pulse, rest pulse, and max pulse. The researcher applies two different modeling approaches. One is generalized regression with LASSO, and the other is a decision tree based on variance reduction. The results? LASSO finds no important predictors. All coefficients are zeroed out. But the decision tree? It highlights max pulse as the most important variable in the model. Interestingly, what's going on here? Why the disagreement? And more importantly, which model should you trust? Let's unpack that. In generalized regression modeling, like LASSO, unimportant predictors are naturally dropped from the model. This approach applies a penalty that shrinks coefficients of irrelevant features exactly to zero. If none of the independent variables are predictive of the target, it won't select anything. It's capable of saying, there's no signal here. But some decision trees behave very differently. Even when all features are completely uninformative, the decision tree will still split. It will always assign at least one variable to the model, even if it's just random noise. Why does this happen? It is because some decision trees are inherently greedy algorithms. For classification tasks, they use Gini impurity or entropy. And for regression, they rely on variance reduction, typically MSE. So even in a dataset where no feature relates to the target, random fluctuations can trick the tree into thinking there's useful structure. The tree then says, okay, that split looks slightly better. Let's go for it. And just like that, you're overfitting noise. There is a way to alleviate the problem. The decision tree implementation in JASP, a graphical version of our language, is more conservative by design, which helps it avoid overfitting to noise. Unlike traditional decision trees that greedily split on any small reduction in variance or impurity, JASP imposes stricter stopping criteria. JASP typically has default minimums for observations per split. If a potential split doesn't create child nodes that meet these minimum sample size requirements, JASP simply won't make that split. This is an example using the same weight data set. So what if we go beyond a single tree? What if we use ensemble methods, like random forests or gradient boosting machines? These models are certainly more powerful and robust, but they inherit the same problem in decisions trees if the trees are based on greedy algorithms. Even if none of the features are actually related to the target, then random forests and boosting will still return something. That is because they're built to reduce training error by selecting seemingly predictive splits, even if those splits are exploiting random noise patterns. Does that mean we should always default to generalized regression like LASSO? Not really. LASSO has its own issues. It assumes linear relationships between the predictors and the target. If your data contains nonlinear patterns, LASSO might completely miss them, unless you explicitly include polynomial terms or interaction effects. It also struggles with highly correlated predictors and may arbitrarily select just one while discarding the rest. This is where decision trees shine. They naturally capture nonlinearities, threshold effects, and feature interactions without needing any manual feature engineering. For instance, analysis of Titanic passenger dataset using the decision tree indicates that there are interaction effects between sex, passenger class, and age. Specifically, if the passenger was a female and held a first or second class ticket, then the chance of survival was as high as 0.9299. If not, it dropped to 0.0701. So what's the recommendation here? Simple. Run multiple models. Don't rely on one method to tell the whole story. And don't base your decision purely on accuracy metrics. Always bring your domain knowledge into the picture. Interpretability, model assumptions, and real-world logic matter just as much, if not more, than a few percentage points of validation accuracy. In this case, a strong understanding of biomedical domain knowledge is helpful. For example, body weight tends to increase with age through early and middle adulthood due to metabolic slowdown and lifestyle factors, but often declines later in life due to muscle loss and reduced appetite. This introduces a nonlinear relationship with age that a linear model like LASSO may struggle to capture without transformation. Runtime and endurance tests generally shows a negative correlation with weight. Heavier individuals tend to perform worse due to the extra load. But that's not always the case. Athletes with higher lean body mass might be heavier and still perform well, highlighting the complexity introduced by body composition and training history. Taking all of this into account, it's understandable that LASSO fails to identify clear predictors. It's trying to force linear relationships onto highly nuanced, nonlinear, and mediated patterns. So, while the decision tree might be overfitting in this scenario, it's also possible that it's picking up on subtle, nonlinear signals that a generalized regression model just can't see. Ultimately, this suggests the need to incorporate richer variables, like muscle mass or training load, and to explore nonlinear models, such as decision trees or ensemble methods, to better capture the complexity of the relationships. Finally, let's hear your thoughts. Have you ever been misled by a decision tree that looked great on paper but was just fitting noise? Or has LASSO ever zeroed out a variable you knew was important? Share your experience here, and if you found this helpful, please pass it along to someone else who's building models in the dark. Thank you for watching.